a little bit late to the conference of Professor Steve SCHEINER. He's a professor of computational chemistry at Utah State University. After receiving his PhD from Harvard University in the 1976 and proceeding to a Weizmann postdoctoral fellowship at Ohio State University, he started his independent academic career at Southern Illinois University, Carbondale. He moved to Utah State University in 2000. His research has centered around various aspects of H-bonds, from their fundamental underpinning to their role in enzymatic activity, from the proton transfers that take place within to their cousins, known as halogen, chalcogen, pincogen, and tetral bonds. So, to our conference, and let's start.
Okay, well, hello to everybody. Good morning, good afternoon, good evening, wherever you happen to be at the moment. So let me share my screen and get started. So what I'm going to be talking about today is proximity effects of substituents on hydrogen bonds. So my co-worker in this was Jordan Lapp, and this work has been published if you're interested in reading about this. And let me first start by just very quickly outlining what is a halogen bond. Clearly, most of the participants are aware of what we're talking about, but for those who may not be, I thought it might be worthwhile to give a brief introduction. So if we start with a molecule like this, and I is the halogen atom, if you look at the electrostatic potential, it looks like this, and this blue color, potential is set up so blue is positive and red is negative. So at the very end along this
Steve,
yeah.
your screen is not shared, so we don't see your presentation at the moment.
Let me try it again. Share screen. Okay, is that shared now?
It's coming.
It's coming, yeah.
Okay, you can start the presentation now.
Okay, so let me get started again. So I'll be talking about proximity effects. Jordan Lapp is my co-worker on this project.
Perfect.
And, so outlining a halogen bond, when we have a molecule like this one, FCCI, we look at the electrostatic potential around it, and you'll see that it has a, get that off. There's a positive hole. So the blue represents a positive color. The red is negative. And so this positive potential can interact with a nucleophile. So for example, ammonia, which has a negative end, which is where the lone pair is. And so down at the bottom, so one of the factors of a halogen bond is an electrostatic attraction plus to negative. Another one has to do with the fact, look at the orbitals. So the ammonia molecule has a lone pair with 2 electrons. The alkyne, it's non-bonding, or rather anti-bonding orbital between the C and the I looks like this. And this shape here, there's no electrons in it, So this overlap allows some electron charge, electron density to transfer from the N lone pair to the sigma star orbital. So a halogen bond has an electrostatic force, and there's a charge transfer piece to it. There's also some dispersion, which I'm not going to get into it at any length. So what happens when we put an electron withdrawing substituent? So this is HCCI, and if we put F here, which is an electron withdrawing agent, it'll pull electrons density from I towards F, and that will intensify that sigma hole that was over there. So that business of electron withdrawing substituents pulling density away from this molecule, which we call the Lewis acid, that's pretty well known. The questions that we're looking at here is how far from the I can this electron withdrawing substituent be and still strengthen the halogen bond? Another issue is, as it pulls the density, is it doing it through space or through the bonds? Is an inductive effect. Then another issue is intervening groups here. Double bonds, triple bonds are an aromatic ring. And yet another issue is two different electron withdrawing substituents, F versus CN, which is even stronger. So some of the issues we're going to talk about related to this is not just the strength of the hydrogen bond, but Vmax, which is the depth of the sigma hole. We'll talk about the density topology along the lines of the talk we just heard, charge transfer, how the formation of this bond affects the monomers, and some spectroscopic aspects. Okay, so these are the systems we looked at. So first, they're the alkynes, where these are triple bonds. So this is one triple bond. This one, we add a second triple bond, and here we add a third one. So we're progressively moving the F or CN further and further away. These distances in these particular systems are outlined here, 4.5, 7, 9.5 angstroms. Another set of systems we're looking at are the alkenes, where there are double bonds, one double bond, 2 or 3. And here are the distances. So we're moving the substituent further and further from the I in terms of number of bonds away, as well as actual distance. Another set of systems is when the I is part of a phenyl ring. The withdrawing agent can be ortho, meta, or para. So of course, it's further and further away in terms of 1 bond, 2 bonds, or 3. And it's also further away in terms of the distance, 3, 5, 6 angstroms. And what about when we put 2 such agents on, 2 ortho or 2 meta? So those are the systems we're going to look at where where the electron withdrawing substituent is either F, as are pictured here, or cyano group. So the calculations are done in a DFT method using MO62X, OG, and with this basis set. For iodine, we use a pseudopotential, which will take into account the some of the relativistic effects. We're going to look at a specific surface, 0.001 AU, which has been adopted as pretty much the standard isodensity surface to look at. We'll look at AIM to quantify the bond strength. We'll use NBO to look at charge transfer between individual orbitals. And we'll look at NMR calculations with the gauge invariant atomic orbital method. Okay, so first, the molecular orbital or the molecular electrostatic potentials. So unsubstituted F and N, where this is sitting on here. And so as we go from H to F to N, or Cn, this blue region is getting more intense. So Cn is a more effective electron withdrawing agent than F is. So the actual maximum is 36, 38, and 50 and these are in kilocalories per mole. So these are just the simple alkynes. And in a more extensive set, these are the Vnecks for a range of systems. So these are the alkynes with 0, 2, and 4 carbons between the I and the R. So R is the electron withdrawing substituent. These are the alkenes, 0, 2, 4, 6 atoms. So each of these just shows the chain getting longer. So this is with H. As the alkynes, as the chain gets longer, there's a slight deepening effect of the sigma hole. So the triple bonds act as somewhat as electron withdrawing agents themselves. In the case of the alkenes, that's not really the case. The double bonds really don't affect the sigma hole. When we now add F on the end, when we go from H to F, it gets more intense. The red numbers are the difference that happens by changing H to F. It gets more intense by 2, but as the F gets further away, it's very little effect. On the alkenes, though, as the F gets further away, it has a large effect when it's close. Now remember, in the alkenes, we have 2 agents. Alkynes, there's only 1. Alkenes, there's 2. So there's somewhat of a doubling of effect. With this cyano group, which is more electron withdrawing, the sigma hole gets deeper and deeper, and the effect is more prolonged. So with 1 triple bond, the cyano group adds 13. Second, it's 9. The third, it's 7. So even with 3 intervening alkyne groups, triple bonds, the effect of the CN is still lingering. The CN also intensifies the maximum with the alkenes as well. So this summarizes those effects that I've just mentioned. Now shifting over to the phenyl ring, same thing, we have ortho, meta, and para, diortho, dimeta. So this is when there's no, just H. When we put F on, it intensifies ortho, meta to para. It intensifies by 4, 3.7, and 3. With the cyano group, it goes 7, 8, and 8. So again, the cyano group has a more intensifying effect. And in both cases, well, in this one particularly, the effect dies off as it gets smaller. Here, there's a little blip that para is perhaps a little more effective than meta. When we put 2 substituents on, 2 ortho or 2 meta, the effect is stronger in both cases. And in fact, it's almost exactly twice what it is. So 2 orthos is twice 1 ortho. 2 metas is twice 1 meta. So there's an additive effect of putting 2 substituents on the phenyl ring. So again, these are just the intensities, the depths of the sigma holes on the iodine. Now we're adding the nucleophile, which we're using ammonia as the standard base. And these are some samples of what these molecules look like. So the ammonia is sitting off on the iodine, pretty much in a linear configuration. So this has a cyano substituent. This has 2 Fs. This is dimeta as just examples. Now we get to the heart of the matter, which is the interaction energies. So this is the interaction energy between whatever the Lewis acid is and the base. So with the hydrogen, the interaction energy is about 7 to 8 with the alkynes. The alkenes, it's weaker, 3.6 to 3.7. So just as in the case of the depth of the sigma hole, the longer alkyne chain has a small increasing effect, whereas the alkenes, it doesn't. Now we're putting on the F and the CN substituents. And as we do that, just as in the case of the sigma hole, putting the F close intensifies the interaction energy, but when it's further away, there's essentially no effect. In the alkenes, remember there's two of them, the F has a fairly large effect when it's close, but it wanes pretty quickly. In the cyano groups, we have a trend that looks a lot like the sigma holes. The CN has a larger effect than the fluorine, and it lingers. It dies out, but much more slowly. The same thing is true in the alkenes. The cyano group is stronger than the F, and its effect lasts quite a bit. Turning to the phenyl groups, again, the patterns look a lot like we saw for the sigma holes. Ortho, meta, para, the effect dies out as we go from ortho, meta to para. Same thing in the cyano group. And in terms of two orthos or two metas, they have essentially a doubling effect. So the pattern of the interaction energies is very similar to the sigma hole depths. And this shows what it looks like if you try and compare these over the length of a chain. So this is the interaction energy, which we're plotting over the reciprocal of the number of intervening carbon atoms. So the number of carbon atoms is increasing as we go from right to left. This is the reciprocal. And at least for the points we have, there's pretty much a straight line. So as the number of carbons increases in the alkenes, the interaction energy is dying off. The alkenes are also dying off, and so is the phenyl, but the slopes are quite different. The alkenes has a stronger 7 slope versus 3.5. So the slope in the alkenes is roughly twice that of the alkynes. And you could say that might be because the alkenes, we have 2 substituents instead of 1. But in any case, this shows there's a predictive power to this and shows exactly how the interaction energy is dying off as the substituent is moved further away. Okay, other parameters we're interested in are the intermolecular distance. That is the distance from the I to the N. So this is the distance in hydrogen when we have no substituent, when we add F, and when we add CN. Again, the red numbers are the effect of the substituent. So when there is a substituent, these negative numbers indicate that the bond is getting shorter, which makes sense. You'd expect a stronger bond to also be a shorter one. And again, the alkynes have an effect which goes down essentially to 0 quickly for F. It lingers more for the cyano group. The alkenes, again, dies off quickly for F, less quickly for the cyano groups, and the trends for the phenyl groups, very similar. Ortho has a stronger effect than meta than para, and the di-substituted effect is roughly twice that. Now we're shifting over to another measure of the bond strength, which is the electron density at the bond critical point as measured by AIM. And all of these are in units of 10 to the minus 4th AUs. So 202 would be in normal language 0.0202. So these are sort of classic ranges for non-covalent bonds. And the bond order increases slightly for the alkynes as we get further away, no effect for the alkenes. When we move to the effect of the F, effects again are about the same. The F's effect is good when it's close, but not when it's further away. It dies off quickly. The cyano group dies off again, but more slowly. So all these trends are very similar to one another. This is the same pattern for the NBO. So what we're looking at here is the charge shift that goes, as I mentioned in the earlier slide, from the lone pair of the nitrogen on the ammonia to the sigma star CX bond. And this is the amount of that. This is in kcals per mole. Exactly the same trends. The effect of the F is only true for when it's close, goes away quickly. The cyano group lasts longer. Phenyl groups, ortho is bigger than meta, which is bigger than para. Same pattern. Another way of looking at what the halogen bond does to the monomer is how much it stretches the bond. As I mentioned, there's some charge transfer into this sigma star bond. That charge transfer into an antibond will lengthen as it weakens the bond. And these show the amounts of that stretch. Same pattern. The effect of fluorine is fairly small and goes away quickly. Cyano group lingers around longer. So the bond stretch is also consonant with the bond, the bond stretch is consonant with the strength of the bond as measured by other parameters. Along with the stretch comes usually will be a redshift of the frequency. But I want to caution you that measuring or identifying a particular frequency is not trivial in these cases because there's a lot of mixing. So you have to take these numbers with a grain of salt. They're not pure at all. And you can see some of these numbers are blue or rather positive, some are negative. So we're going from red and blue shifts. So the CI stretching frequency is hard to identify explicitly because there's so much mixing. So these CI stretching frequencies are not really a very effective means of looking at these bond strengths. Now in hydrogen bonds, some of the techniques that have shown very good usefulness is the shifts in the chemical shielding of various nuclei. In particular, in hydrogen bonds, it's the proton. Well, here we're not talking about hydrogen bonds, we're talking about halogen bonds. So the I is the bridging atom. And this is the change in its shielding in these same patterns. And there's some erratic quality here. When the F is close to the I, is actually a small increase, whereas when it gets further away, it gets to be deshielded. The CN has some erratic changes here. So unlike in the case of hydrogen bonds, where the shielding or shift of the central bridging proton has proved to be a pretty effective means of gauging the strength of the bond, you probably cannot say the same thing here in the halogen bond, where we're talking about the I atom shift. Another atom that's used in hydrogen bonds is looking at the atom which is directly bonded to the bridging hydrogen. In this case, that's the carbon that's bonded to the I. Here is a little bit better correlation with the interaction energy. It's still not very good. We do see that the CN effects last longer than the F effects. In the phenyl, well, ortho is greater than para than greater than mara. So these effects are not necessarily consistent. So the C13 shift would probably not be the best gauge of the strength of an interaction. On the other hand, the N, this is the N of the ammonia that we're talking about. So it's on the other molecule. And the shift that takes place on that nitrogen is downfield. So you can see all these shifts are negative. And so minus 25 with the alkenes, 22, and the effects are here pretty good. So the deshielding of the fluorine goes away very quickly. The deshielding of the CN stays longer, although you do have this anomaly of a positive quantity here. In the alkenes, it seems to last a little bit longer than some of the other effects. And in the phenyl group, now we have the ortho greater than meta, greater than para that we were seeing before in the energetics. So there does seem to be a decent correlation between the interaction energy and the change in shielding of the nitrogen on the nucleophile. So this is the interaction energy as the horizontal axis. The change in shielding on the nitrogen is what's being shown here. There's not a great, but a decent correlation here, correlation coefficient of 0.86. So it's possible that the chemical shielding of the nitrogen, which is on the nucleophile, may be a useful indicator for experimentalists to at least approximate the strength of a halogen bond. So the conclusions of all of these things, if you simply elongate an alkene by adding more CC units, so this is just with a hydrogen, that doesn't affect the CI group. Although if you use triple bonds, there is a small increment that arises as the triple bonded alkyne monomer gets longer. You get a stronger effect if you add an electron withdrawing agent. In this case, we considered F and CN. And this effect does come down as the substituent is moved further away, which is pretty much what you'd expect. F substitution has a much smaller effect than does cyano substitution, and its effect lingers for a shorter distance as you move it away. With the cyano group, you can move as many as 6 carbon atoms away, and you can still see the effect of that cyano group, which is transmitted through a longer chain. The electron withdrawing substituent strengthens the CI halogen bond also when it's added to iodobenzene. And generally its effect goes down with distance, with ortho meta para being the trend. In case of the alkenes, since you're adding 2 of these substituents on the end of the chain, we are getting a larger effect than with the alkynes, which only have a single one. And the aromatic systems are least sensitive to the substitution. And the effects on the energetics are not just the energetics. These same effects are seen in the sigma hole depth, which we looked at first, the electron density of the AIM bond critical point, the amount of charge transfer that's taking place, and the changes in the NMR chemical shielding, although it's really only something that you see on the nitrogen in any kind of aromatic way. So with that, I'll conclude what I'm talking about, and I'll take some questions if there are any questions from people.
Thank you very much for your